This video will introduce the integral test to decide whether or not a series converges or diverges. So we've seen a famous example. Let's start off with the harmonic series again. We saw that in our last video. The harmonic series is the sum 1 over n. Starts off as 1 plus 1/2 plus 1/3, and so on. We've already seen that this series diverges, but I'd like to give you another reason why this series diverges using a geometric argument. So let me draw an axis system. The x-axis will be 1, 2, 3, 4, 5, and so on. And I'm going to scale my y-axis a little bit differently so the picture looks a little bit more clear. So the scale will be different. This will be 1 way up here, 1/2, 1/4, and so on. I'm going to represent the terms in my harmonic series with areas of rectangles. So the first rectangle I'm going to draw is going to have height 1 and width 1. So my axes are scaled differently. It doesn't look like it, but this is actually a square. It has height 1 and width 1. So the area in this square is area 1. Next, I'm going to draw a rectangle of area 1/2. So I'm going to go height 1/2, and width 1 to give me area 1/2. Next, I'm going to draw a rectangle of area 1/3. So height 1/3, width 1, the area in here will be 1/3. And I'm going to repeat this process. So height 1/4, width 1, area 1/4, and so on. So the area in the boxes, the area in the rectangle, is my harmonic series. I'm going to draw a function that passes through these points. So I'm going to draw a function that goes like this. That's the function 1 over x. Because if I plug in 1, I get a height of 1 over 1. If I plug in 2, I get a height of 1/2, and so on. So the key observation is to realize that my harmonic series, the sum going from 1 to infinity of 1 over n, that's the area in the rectangles. And the area in the rectangles is bigger than the area under the graph of 1 over x on the interval from 1 to infinity. All I'm saying is that the area under the curve, under the red curve, is smaller than the area in the boxes. You could even see there's area above the curve. So there's more area in the boxes. And this is the integral from 1 to infinity of 1 over x dx. That's an integral that maybe you should know how to do from your experience in the previous calculus course. Whenever you see an infinity up here, the first step is to write a limit as t goes to infinity. The integral of 1 over t, 1 over x dx. This integral is log t, so this is the limit as t goes to infinity, log t, and log t has limit infinity. So that proves the harmonic series diverges because this harmonic series has to be bigger than a divergent integral. This is the idea known as the integral test. You could sometimes relate a series, a sum of numbers, to an integral to decide whether that series converges or diverges. So this diverges. I'd like to do another example with this same idea. So let's consider the sum, n going from 1 to infinity, of 1 over n squared. So this is 1 over 1 plus 1 over 2 squared plus 1 over 3 squared, and so on. Again, I'm going to draw boxes. I'm going to draw boxes with areas, what I want them to be, matching the terms in my sum. This time I'm going to do it a tiny bit different, however. This time, I'm going to, so there's 1, 1/2, 1/4, there's 1, 2, 3, 4, 5, 6, and so on. This time, I'm going to shift my boxes over just a tad. I'm going to shift my boxes over a tad. So I'm going to draw my first box in between 0 and 1 instead of 1 and 2. So I'm going to draw my first box this way. So the area in that first square actually is 1. Next, I'm going to draw a rectangle with this area. So that's 1/4. The next box will be 1/9. 1/9 is pretty small, so here, and so on. So this will be 1/9. And the numbers are getting too small to write in, but those are my boxes. Next, I'm going to draw a curve that passes through the right-hand endpoints of my rectangles. So I'm going to draw this curve that goes like this. That's the graph of 1 over x squared. 1 over x squared. So this picture says that the area under the graph of 1 over x squared is more than the area in the boxes. So this time the inequality goes the other way. This is less than the integral from 1 to infinity. Well, actually, you know what? The integral from 1 to infinity doesn't account for this 1 here. So maybe technically I have to say this is less than 1 plus the remaining terms. The integral of 1 over x squared dx. Let's do the calculation. So this is 1, and then I have an infinity up here in the limit of an integral, an improper integral. Every time you see that, first step, write things down as a limit. And then some students like it when you're integrating to write this as x to the negative 2 dx. Some people like to do it that way because it makes it more clear that I have the limit as t goes to infinity. So this term here, when you integrate, I think you'll get negative x to the negative 1. You add 1 to the exponent. And I evaluate at 1 and t. So this is 1 plus the limit as t goes to infinity. So you plug in t, I get negative 1 over t, and I subtract and I plug in 1. So I get 1. Then when you take the limit as t goes to infinity, this term goes away. I end up with 1 plus 1, which is 2. So 2 is a finite number. It's not infinity, it's a finite number. Meaning the integral from, this term right here, 1 plus my integral, is the area under the curve. That is a finite number. So therefore my sum, my infinite sum, also has to be a finite number. So therefore, my sum converges. It converges. These numbers do not add up to 2, they add up to a number less than 2. It's not clear what number that actually is, but I do know it's a finite number. So this gives us the idea of the integral test. Let me state what it says. If you have a function that is positive, so I don't want anything going below the x-axis here. Everything has to be positive, just like the red graphs here. So if I have a positive function that is decreasing, so going down like these two pictures, and when I plug in a value n, I get the term in my series, then the infinite sum, an, converges if and only if the improper integral of f of x dx converges. So I'm writing down the general statement that we used in these two examples. I'm not going to prove why this is true. The proof is basically the ideas in these examples, but you can use the integral test to decide if a series converges or diverges. We'll do more examples in the next video. Thank you.